Lamellipodium is the title of my talk. The lamellipodium is a motility organelle for rolling cells, and over quite a number of years now, we have in a group here in Vienna, we have worked on modeling this organelle, and a certain model, or say a modeling approach rather than one particular model, has developed, and we call it the filament based Lamellipodium model. You will see filament based, this extra filament based here is motivated by the fact that different from other continuum models for this organelle, we don't use kind of standard, more or less off the shelf continuum models, but we try to develop the model from a more microscopic perspective. My talk today is on ongoing work, and actually I do not really have new results to present. Honestly, I will. A big part of the talk will be a review of what has been done and of all the results, but that is necessary to motivate what we are doing now. Actually, together with a PhD student, Jeremy Arqueles, who is in Vienna with the fellowship of the Austrian Agency for Education and Internationalization. So, let me get into it. I hope this works. Yes, seems to look good. So, first, idea: what is the lamellipodium? Certain cells, if you put them on a flat substrate, so this is actually here we're talking about taking a cell which is usually part of a multicellular organism, take it out of its natural environment and put it on a flat substrate. And then some of these cells have the ability first to hold on to this substrate by building adhesion links, and then to crawl along these substrates. And what you see here is a cell which is called the fish keratocyte. It's a cell which typically is like a skin cell, but it lives on the scales of fish usually. And so you see this one individual cell, and here this is the cell body, and all this flat region here, that's this lamellipodium. For the fish keratocytes, different to many other cells, the lamellipodium usually becomes a very wide, big structure, and this is why the fish keratocyte is a model organism for studying the lamellipodium. In this second picture here, it's just the same photograph, just with some imaging tool. The cell boundary has been pointed out, so you really see the periphery of the cell, and you will see better this lamellipodium. You see that this keratocyte cell takes a characteristic polarized shape, where the lamellipodium only exists on one side of the cell, and this side where the lamellipodium is developed singles out the movement direction, actually. So this keratocyte would actually, that would be a moving state where the keratocyte moves in this direction. And the lamellipodium has both the function to kind of glue the cell or hold the cell onto the substrate, so that it doesn't float away, but also it's the movement organ, as I said. The question is, how does this lamellipodium look like? So how does it work? There has been a lot of modeling, and much of the modeling has not gone very deeply into what is really inside the lamellipodium, but has basically, from observations, how it works and what it does. Certain continuum models have been written, which are able to nicely reproduce what you see in terms of moving cell shapes and so on. We have been going in different ways, and let's look at more closely what is inside the lamellipodium. And this is a story which has developed over the last more or less 10, 15 years, where with the increase of using electron microscopy for looking at the inside of cells. And in this period, a very detailed understanding of what the structure of the lamellipodium is has developed in biology. However, already since quite a long time, there have been certain ideas what's going on in the lamellipodium, and this cartoon, which I put here on the right, is actually rather old, and it collects some of the ideas what's going on. The main structure supporting the lamellipodium is filaments, polymer filaments of the protein actin. So these pink, with two shades of pink sticks here are should represent actin polymers. Actually, they come in two colors here, but this is only to outline that you have this kind of crisscross structure with some filaments which are oriented more to the right and other filaments which are oriented more to the left. Actually, these colors should be different here, I would say, and also this from my point of view. Anyway, the idea is there is this crisscross network. The colors just are an indication for the direction of the filaments. However, this is not all. The whole structure relies on the interaction with quite a big number of other proteins. So, for instance, you see that this network is branched. So you see a lot of branches, and where the branches happen, you see this little blue symbol. The little blue symbol is a certain protein complex which is important for the branching. And you see other symbols like these green Ys here, or these gray things. These are proteins which make connections between different filaments. So the green stuff between grossing filaments, the gray between parallel filaments, and all these provides a certain structure to the network. And then this is not a fixed network which is just sitting there, but it is very dynamic. So what actually happens is that typically these filaments keep polymerizing, and actually they do that close to the outer edge. So this edge here corresponds to the yellow line here in the picture here. Is the outer edge, and there is a whole complicated protein machinery which does lots of things, but and these proteins sit on the cell membrane. But one important thing they do is they regulate the polymerization of the filament. So little monomers, individual actin molecules, like these little dots here, are added to the filaments. And what that produces is that the whole network is pushed backwards all the time. So this whole network, you have to think of, is moving away from this leading edge continuously. And of course, that the cell would get bigger and bigger and bigger. The lamellipodium would get wider and wider this way. But in order to stabilize the situation, create a homeostatic situation, what also happens is a degradation of the filaments. At the end, there is these little silver symbols, which symbolize yet another protein, which regulates the cutting of filaments. So you cut off the pieces at the end are cut off. So there's all these mechanisms going on. I have so now I have described already polymerization. Polymerization, that was the last thing which I said. Branching, I said there are branches. The idea of the branching is that the branching is responsible for creating new filaments. So new filaments are created by branches, and these branches typically start also very close to the leading edge, but then they are pushed backward. So you see them all over the place, also in the back, but this is just because they are pushed away from the leading edge. The opposite process, so to say, is capping. So filaments can be deactivated by a protein being put at the end, and then no more polymerization takes place, and the filament more or less is out of the game. mechanical processes which are going on is also filament bending. So these filaments are sticks. Here they are shown as straight, but typically they can be bent by forces. I have talked about cross-linking, blue and another green and gray symbols here. Cross-link filaments. There is substrate adhesion. The whole network is connected to the substrate. This is not shown here. I said that already. To hold on to the substrate. About actin myosin contraction, I will not really talk much here. Another process is filament repulsion. Parallel filaments. There's typically a repulsive force between parallel filaments, and the reason is that these filaments carry some electrical charges. So these filaments are actually charged. And since charges repulse each other, parallel filaments typically there's a certain repulsion. And then the whole environment of the filaments is also important. In particular, the whole structure is surrounded by a cell membrane, and the bending of the membrane and the stretching of the membrane can also be important for what's going on. So the idea of this filament based Lamellipodium model was to have an account of all these things. I showed before these light microscopy pictures, and I said there was this huge development in microscopy, and in particular we have for a long time worked with a group of Big Small, who was one of the pioneers of electron microscopy for these structures. And what you see here is some result of electron microscopy, and actually it is only a small part of the information here, because the information really is 3D information. So you get really three-dimensional pictures more or less from this electron tomographic treatment of these electron microscopy results. And this is just a 2D projection. And the amazing thing is now really you see the individual filaments here in these pictures. And in the beginning of our cooperation, we have also worked on image processing. And one result of the image processing is the picture in the middle, where you actually identify the filaments which you see. And then as soon as you have done that, you know a lot of the structure and you can do statistics, right? I mean, of course, we do not want to describe this structure in detail. You see, it's rather wide. There is a lot of stochastic, a lot of noise perturbations, but you can do statistics. And one statistics, for instance, is take the leading edge here, has a certain direction, and now just make a statistics of the directions of the filaments relative to the leading edge. And what you typically get is a picture like this here, where you see that there are two peaks. And this is going to be experimental evidence of the cartoon which we saw in the beginning, which said that there are basically two directions of filaments. And actually, the picture fits together well. There are these two peaks. The distance between the two peaks is roughly 70 degrees. And it's well known from in vitro experiments that this blue stuff in the picture before, that these protein complexes, they make branches, and if you don't touch them, if you leave them alone, the equilibrium angle between the filaments, these branches is roughly 70 degrees. So all this fits pretty well. So that is the kind of experimental evidence here. And built on that experimental evidence, we have tried to build a model. And for the modeling, of course, we have to do some assumptions, right? The question is, we wanted to do a model based on filaments, but it would be very hard to get something interesting if you would try to model all these filaments in detail with all these variations in positions which they can have. So the most important assumption we made for our modeling was to idealize this picture here to a sum of two delta distributions, more or less. Let's say, see, you have these two pronounced peaks. We say we replace these two peaks by a sum of two deltas. So we allow only two classes of filaments, which you see here in the middle, this is actually a simulation result of our model. You see these two classes of filaments in red and in blue. They have locally, right? They can be bent, and of course the direction varies when you go around here. But locally, if you look at one point here, you only see two directions of filaments. That is the idea. So this is this idea of having this these two pins. And actually, this picture here is is just post-processing of our model. Our model is a continuum model, and it provides results for kind of typical filaments in this structure, and including a length distribution of filaments. So there you have all filaments start from the leading edge, and they go backwards, but they can have varying length. And so our model basically produces a distribution of filaments, and the picture here is produced by sampling from this model. Yeah, I don't want to go into the details of all what is around here. It's just more or less repeats things which I have said before. It's just details on all these processes which we want to model. The model has two aspects, and one aspect is the mechanical aspect. So where are the filaments? What is their shape? How do they move? That is the and what are the forces acting? So there is a mechanical aspect, but there is also a chemical aspect to the model, and that is connected to the polymerization of the filaments, the depolymerization of the filaments. These are chemical processes, or the branching, or all these things, branching and so the nucleation of filaments by branching, but also the capping. So all these are chemical, the chemical processes. The mechanics deals with a mathematical unknown, which is this capital F here. The capital F describes the position of filaments. It depends on time, of course, little t. It depends on S and on alpha. This is a two-dimensional model, so the two parameters, spatial parameters, so to say, are S and alpha, but actually they're not so much spatial parameters, but Lagrangian variables. The alpha is an indicator for the position of the filaments, or a counter of filaments. Right? When you go in the picture below, when you go around here along the leading edge, this is what varies with alpha. So alpha also, or you can also say alpha is a parameter along the leading edge. And along the leading edge you pass the filaments, so it's kind of a counter of filaments. The S is goes along the filaments, so it's a parameter along the filaments. Actually, it's an arc length parameter. And so when this capital F, the vector in R2, so it gives a position in R2, and F of alpha and S is the position, you could say, of the filament number alpha, or better, the position of the polymer number S of the filament number alpha. Okay? And so S is a Lagrangian variable along the filament, but also you see here in this assumption it's arc length. So we assume that it's arc length, and the idea and the assumption that arc length is the same as a Lagrangian variable is actually an inextensibility assumption. So the filaments are inextensible. Now you have this complicated model. I will maybe explain a few of the terms here, but not all of them. It is, there is too much in it. For instance, this first term here. This is, you see, a kind of time derivative. Actually, it is a material derivative, I lied to you a little. The alpha and S are not quite Lagrangian variables. In particular, the S is not quite a Lagrangian variable because we always start counting with the S at the leading edge. But as I said, by the polymerization, the filaments are always pushed inside. So actually they move relative to the leading edge. And the time derivative of F is not quite a material derivative, but you have to shift it by this definition here, where the little d is the polymerizations. Okay? So this is really time, this is really the velocity of the filaments above ground. So this is a friction term. And there is a friction coefficient. And where does the friction come from? Actually, it comes from the fact that the network keeps building and removing connectors to the substrate. And this permanent process of building and removing connections can be modeled from a more macroscopic point of view by friction term. And then there is, so mu A is the friction coefficient, and then there's also this eta here, and the eta is actually also a function of T alpha and S, and it can be seen as a density in the Lagrangian variables. And actually, the F, as I said, is the main unknown concerning the mechanics of the problem, filament positions. The eta is actually the second main unknown of the problem, but it is connected more with the chemistry. The eta is influenced by nucleation, so building new filaments, by the cutting of filaments, by the polymerization, which all influences the density of filaments. So you have a filament density here. So this first term, and A for adhesion, is a friction term. It's friction above ground. The second term you will recognize is a very simple bending model. So this is mu B is kind of bending stiffness, and so this fourth order derivative with the density also in the middle here is a bending model, actually like the filaments are modeled as Bernoulli beams will be the bending term. The third term here is a term which comes actually from this constraint of inextensibility constraint. It is kind of a term which has a longitudinal force with the lambda here, but the lambda is just the Lagrange multiplier for this inextensibility constraint. And so we continue. The following terms I will not go into as much detail anymore. So there is, for instance, a pressure term. This whole second line comes from the pressure. Pressure comes from this repulsion of filaments because of the electrical charge which I mentioned. The remaining terms come from the connection between the two filament families. The other family is, so this is for one of the equations for one of the two families, red and blue, remember? So this is for 1 and 2, and the other family has the star. So what you see here, for instance, is the friction between the two families that comes again for building and breaking connections between them. This term here, it's turnabout angle. So phi is the angle between the two families, and phi naught is an equilibrium angle. And I said there are these 70 degrees, which could be the equilibrium angle for the branches, for instance. And so we assume there are these, there is an equilibrium angle between the two families, and this term is actually a turning term. You see here a force in the orthogonal direction, right? D is F the tangent vector, so D is F orthogonal is orthogonal of the tangent vector of filament. So this is a turning term which tries to produce the equilibrium angle. As I said, I do not want to talk much about actin-myosin interaction, and this means I do not talk about the last two lines here, which actin-myosin interaction. Maybe I say it in words. Actin-myosin interaction is well known to many people from who deal with muscle contraction. So that's the main mechanism of muscle contraction. But it does not only occur in muscles, it occurs in many cells. And myosin filaments are trying to make the two families of filaments count in opposite directions. So this is why there is an equilibrium angle P here. and they also produce some kind of friction, however, shifted by a certain velocity, Vm, which is the contraction velocity. The myosin tries to contract the actin filaments, and that is useful. Okay, so you see, quite complicated model. So what we have is we have two versions of this PD, and the PD is actually a system of two PDs, right? It's a vector equation in R2. So we have a system of 4 PDs here, and the eta and the eta star for the other family are actually input into this system. So here, F can be seen as the unknown, and the etas can be considered as given. The etas will not be so important for me through the rest of the talk. Therefore, I will not write any equations for about how they are modeled. I just give you some keywords, what is important to avoid. So, first of all, we assume the first question is about the length, or I should rather say first, sorry. The eta actually carries two informations. It carries information about the number of filaments, so how dense the filaments lie if I go along the leading edge. But they also carry information about the length distribution. So these are actually two different things. And so let's first, how do we model the length distribution? The length distribution is modeled kind of as a balance between polymerization, which tends to make the filaments longer, and fragmentation, so cutting of filaments, which tends to make them shorter. The filaments all start at the leading edge and point and adhering inwards in the cell. Polymerization is assumed just as a growth process with a certain given rate at these ends, and the fragmentation is actually modeled as a process of random cutting of the filaments, random cutting at random times and random positions. And whenever you cut off a piece, then the end which is inside is basically thrown away. It's not part of the game anymore. This process can be modeled by a fragmentation transport equation, where you have both fragmentation and transport, and actually this equation, if you do a reasonably simple modeling of that, what you can do is you can compute equilibrium states of this model explicitly. And actually what we assume here is that this process is always in equilibrium, and we just use the explicit equilibrium state for the length distribution of the models. So this is the length distribution. The number distribution comes from, I have already said, branching and capping. Branching is the process of nucleation of new filaments, branching away from old filaments, and capping is the process of throwing away filaments, because when they are capped, they are deactivated, not part of the game. So filaments are created and lost, and however the process is, to describe the process geometrically is not so easy, because if you look at the picture down here, which is a very old cartoon by Big Small, drawn by himself, you see that if you have the leading edge here, right, and these filaments grow, and then you look at the leading edge a little bit later, then you see that the growth of the inclined filaments actually has as a consequence that the one family of filaments, that the ends move to the left and the other one move to the right. So you have this, what the biologists call the lateral flow of the filament ends along the leading edge. And that has to be taken into account when you do the balance of the nucleation and the capping. And the nucleation is actually we model by a mechanism type kinetics, because if you remember the little blue symbols in my picture in the beginning, this protein complex is called the actin-3 complex. That is kind of a limiting factor in this. It works works, it's like if you have heard about enzyme kinetics and the mechanics making models like enzyme kinetics, the R2-3 complex plays the role of the enzyme, so to say. So you use a mechanics making type model. However, it's connected with this movement along the filament things. And actually, just this submodel here gives rise to some interesting mathematics. There is the model becomes then a hyperbolic system with the nonlinear reaction terms, and actually we have there's a separate publication of this together with my former student Angelika Mannhardt, where we have analyzed this submodel and actually shown that we get convergence to steady states. So for the biologists, it's a mathematical proof of homeostasis of the system, of the actin filament system, so that you get convergence to a steady filament length and number distribution, or not number distribution, sorry, length. But both these go into this eta. If you normalize the eta such that starts with the value 1 at the leading edge and then goes down, that gives the length distribution, but then it's multiplied by a certain number, which is basically the filament length. So, all this together is this model. I have not written down the equations for the full model because I have not written the equations for eta. I have not given you the boundary conditions and other details. It would just take too long to see that already much of my time I have used. So I will just end this long introduction basically to what I want to say later by showing typical simulation results, what you can do with this model. So first concentrate on this row of pictures on the left. These are stable shapes of cells which you get from this model under the influence of a chemotactic signal. We heard about chemotaxis in Weinstock just before, so I don't need to explain. What you get here is a chemotactic signal from the right. And what we do here is we think about how is this chemotactic signal translated to the inside of the cell. And what is well known is that cells take in such a signal and then have a tendency to concentrate inside the cell. So just to take, you receive the signal at receptors at the periphery. The idea is that there is more signal on the right than on the left. With and the first simulation is just the idea is the signal is just translated, just taken to the inside and directly acts in the inside. And how does it act? It acts by increasing locally the polymerization velocity. And then when the polymerization velocity is increased, the length of the filaments become bigger. So you see the lamellipodium here is wider than here. And that produces a shape change of the cell, but also produces movement. Because there is this this friction with the ground, and so it is kind of the right part tries to pull the cell to the right, and the left to the left. And since there are longer filaments on the right side wins, and this cell will move to the right. And now, if you change how the signal looks inside, and what we do in this pictures B and C is that to concentrate it more and more at the front. Here in the middle is the back, and outside is the front. So we concentrate it more and more to the front. And what you see is you get, change the cell shape, which gets quite often. Right? The more you concentrate the signal, the more longish the cell gets, which is not really a surprise. The good thing is you can get this just with this all computers with the same one. The final idea here was to say maybe not the polymerization speed is influenced, but the branching speed is influenced, so that you do not get a wider network, but a denser network. And it also works, you also get a moving cell, however, again, with a deflection. Okay, so this was one type of experiments, and this picture here is kind of from our ultimate simulation. Here we have taken 14 cells, all modeled with this model, with some number of additional effects. In particular, you have to model how the cells interact with each other. There is, of course, a volume exclusion part to the model so that they don't overlap, but there's also cell-cell adhesion, as you can easily see from here. Actually, the middle red symbols here show where the adhesion and the strengths of the adhesion. And what you have here is a simulation where we have put everything which we can do in one simulation. In particular, these yellow and red lines are level sets of a chemotactic signal. So you see the signal originates from this point here, and the cells are drawn in this direction, and then there is this dark and white background, and that indicates that the substrate has varying adhesion, so the adhesion is high on the dark parts and low on the light parts. So what the cell, what you see basically, this whole cluster of cells is more or less pulled by these two ones who sit on the high adhesion parts, and they do. And the cells here in the middle, they don't have much of a chance to react to the chemotactic signal, actually, because they don't have room for that. But the whole cluster moves towards this, towards the chemotactic signal. And now, this picture is the main motivation actually for our present work. The point is that this is a very big computation. To compute the dynamics of this situation, it's really a big computation. And but it shows in principle that the model is well suited for computing monolayers of cells. However, when you want to compute monolayers of cells, you don't want to compute 14 cells, you want to compute hundreds or thousands of cells. And so the model is still way too complicated for that. And that is the main motivation for the rest of the talk. And so, as I said, I don't really have results. I have just some ideas and some steps of what we are doing. The first step is to simplify the mechanics somewhat by assuming that going to the rigid filament limit. That means we assume that the bending rigidity, the resistance against bending is very strong. And when you remember the equations which we had before, of these equations now I only keep the bending term, and I have to keep the term with the Lagrange multiplier, because the size of the Lagrange multiplier will depend on what's going on here. So this has to be kept. But all the rest of the equation I take as small. So epsilon you could see is kind of a ratio between the bending stiffness and all the other important parameters. And then here I also wrote the boundary conditions. The boundary conditions basically say that there are only small forces compared to the influence of the bending rigidity. So in the limit, when this epsilon parameter goes to 0, there is no linear force on the filaments. And we always assume that at the ends there is no turning force. And now if you pass to the limit in this model, or you look at the limiting model with epsilon equals 0, then you see what you get is something simple. You get straight filaments, as you can expect, right? And so the filaments are now can be parameterized only by where they are at the leading edge, s equals 0, and by a direction, angle phi. And actually, what you can do, you can you see that there are two invariants here. There are two ways to make two functionals which make the left hand side equal 0. The first is just integration, and the second one is just multiplying by f of orthogonal integration. So this more or less is connected to a linear force balance and torque. And by doing these operations on the equations and then passing to the limits, you get a vector equation here, a scalar equation here, and these are the equations which determine these parameters fr, which is a vector, and the angle phi. Okay, so so that is a way to simplify the model a lot. The S is completely gone, and we only have to go around, and that is what I mean by going to an active curve. However, there is a downside to this, or maybe first I talk about very short heard about the different for doing this. Actually, the whole model comes from a variational formulation. And actually, the whole model can be written in a variational formulation if you do an appropriate time discretization of the friction terms. Maybe you know that gradient flow models can be written at the limits of their Euler discretizations, and then at each step you do a minimization. And something like that you can also do here. And here you have two contributions to the energy, and this is the bending energy. As we saw already before, minimizing it doesn't produce a unique solution, but you get an explicit form of the minimizers of this. And now, of course, the simple thing to see that when you want to minimize here, what you can do is just to first minimize this, and then plug the minimizer as this second part of the energy, and that will produce the limits of the minimizers. And that is a different way of doing the same of what I did in the last slide, but computationally this is actually a favorable. So this is one of the things we do. Two more things I want to say. One thing is that doing this, what I said before, actually it does not produce very nice results. And the reason is that you get lots of terms with integrals over S, which you cannot compute explicitly, and which where you do not have explicit enough information to see what kind of equations you get, and so on. So what we do additionally, or what we try to do, and this is actually why I do not have really final results yet, is we do a certain simplification by looking at short filaments, capital L, or the length of the filament, so looking at short filaments. But the problem is, well, basically all the equations which we had before, maybe you remember here, there's an L here. L is the length of the whole simulation domain, so everything more or less goes away with L to 0. So what you have to do is you have to scale the various constructions, and it's very important how you scale them relative to each other, what you get. So I say here, if you try to do the simplification, you open a kind of Pandora box, and unfortunately we do not have a very conclusive final result, which terms how we want to do this relative scaling. And this is why I cannot produce any final results here. Maybe just to get some idea, I give you the ultimate simplest one which you can get, but it is for several reasons not very useful. So this last thing I want to show you, the simplest models would be that you get such an equation for the capital F bar. So this is basically just the F bar is the position of the filament at the leading edge. So this is just the parameterization of the leading edge, you could say. And what you get here is you get a friction term, and here you get the normalized tangent vector, right? Remember, alpha was the parameter along the leading edge, so you get the normalized tangent vector multiplied by a rotation matrix. Right? So this would be, so what would this give? This just gives and V is the polymerization velocity. So this just gives the growth of the cell in a certain direction, in a certain angle relative to the leading edge. So you all know maybe the flow of curves along the normal, and here it's just not the normal, which is given about a certain direction. So that would kind of be the heart of the model which you get at the end. However, this is not a useful model for what you want to do, so there needs to be more things for several reasons where I don't have time to go into detail. And so that is just an basic idea. Thank you for your attention.
Okay, thank you. So let's begin with questions. Are there questions in the audience here in Paris? Okay, so I begin. So when you I'm trying to think of the final model, and I'm trying to think of the cell moving, evolving in time. So what if you take this one? So how would it move? It says it's just a curve.
So the R, as I said, is a fixed rotation matrix, right? So that each point on the periphery just moves in a direction with a certain speed v in a direction which is in a certain angle to the tangent vector.
Okay, maybe I'm confused. At the end of the day, don't you want the whole cell to move? Or is this a description of the inside, what's happening inside the cell?
Yeah, this is part of what I said, that this is not a complete model. What this model, if you would do that, only that, the cell would get bigger and bigger.
Oh, I see. I see.
In all directions. So the least you need to add to this is a term which comes, say, from a area constraint.
Yes.
And that would give a Lagrangian multiplier, which puts a normal flow, an inward normal flow, to keep the size of the cell. And then when this V, this polymerization velocity, varies around the cell, so it would typically also depend on alpha, then you will get that, relatively speaking, that some parts of the cell move outwards and some inward, and that then keeps the flow.
I see. I see. Okay. Thank you. Are there other questions in the audience? And are there questions online? I don't have a computer here.
I did not see any so far.
Okay. Yes. Yes.
I did not see.
Good. Thank you. Okay. So then,
Check on YouTube.
Please. What did you say?
I was checking on YouTube as well.
Oh, you were checking on YouTube. Oh, I see. Yes. The two. Okay. Good. So then, thank you, Christian. Thank you again.